Okay, Mr. Watson here, and in this video we're going to discuss the vascular shunt mechanism. And I'm probably also going to add on the end the vasomotor control. Okay, quite similar to the cardiac control center. But anyway, first up, the vascular shunt mechanism. Now, what the vascular shunt is, it's the redistribution of cardiac output. But first we need to understand is what is the natural distribution of cardiac output, and this is at rest, okay? So where the blood is distributed to in the body at rest and how it's redistributed during exercise, okay? So as we know, at rest, cardiac output is approximately 5 litres per minute, and we know this can rise during exercise, which we'll come on to in a moment, okay? At rest, what we need to understand is our body primarily serves to digest, filter, and excrete, okay? So, therefore, the vast majority of blood, of oxygen and the nutrient-rich blood from the plasma is required around the organs, and almost 75% of that blood it is required for the organs. Okay, so let's take a look at how that looks and put some context to it. So we're going to put muscles right at the end there, because ultimately we're going to be focusing on the redistribution of blood during exercise. Obviously it's A-level PE. Okay, so let's take a look. So we've got blood going to the liver, and it's the liver/gut, and we can focus on the digestion system, okay? And we've got around 25% of blood going there at rest. And what I should say here is these are basically numbers from a textbook. These numbers vary depending where you go to get your information from, but the general thing we're looking at here is how there's a massive shift in the muscles to the blood to the muscles during exercise, okay? So we don't need to get picky around 25%, 20, 23, etc. We're just understanding a concept here. So around 25% to the liver and gut. Now the heart has its own blood supply, the coronary blood supply, okay, the coronary vessels, and that gets around 5%. The kidneys get around 20%. Bone, and you might see this as other, again, some diagrams don't show bone or other, but I've put it on here, around 5%. The brain, 15%. Okay, obviously we don't want to be cutting blood flow off to the brain, we can have a stroke. And then the skin, okay, the skin also receive blood to help us cool down, etc., around 10%. Meaning at the muscles, we have 20%. So whether obviously the bone, not an organ, so this is where we get around 75% of blood at rest going to the organs, okay? So out of that 5 litres of blood per minute, cardiac output, 75% of it goes to the organs, okay? Now, when we start to exercise, there's a demand for oxygen specifically from the muscles. Okay, so this demand steps up and the muscles want more, basically. And the more intense the exercise gets, the more the muscles need. Okay, so we're just going to focus on 20 litres per minute, but this could be 40 litres per minute for an elite athlete. It could be 30 litres per minute. Again, we're talking about percentages here. We're just looking at the concept. So then, here's how the blood is redistributed. Okay, we drop the liver to around 1.25%. Now, no matter how hard we exercise, the heart maintains its own blood supply. So we've got 4% there, so a 1% difference, but that blood supply to the coronary vessels, that's being maintained. The kidneys drops to 1%, bone 1%, brain 2.5%, and the skin 2.5%. Now that number can change depending on the skin. Again, these are just averages, meaning the muscles at the most intense exercise can get up to 88% of that oxygenated blood. 88%. So you can see there we've had a massive redistribution of cardiac output. Now I'm going to show you it in different visuals. Okay, it's basically the same information. On the left, in a pie chart, we're going to focus on rest. Redistribution of cardiac output, or the distribution of cardiac output, I should say, at rest, and just the same percentages from the last slide. Okay, so muscles getting a 20% chunk, and the organs getting 75% of that blood. Now if we look at the redistribution during exercise, and I'm going to show in a bar chart this time just so you can see it across different visuals, and you look here, much more restricted. Okay, as we know, the coronary isn't budging, it's maintaining its blood flow, and the muscles up to 88%. So I just wanted to present that information to you differently, but the main concept we're understanding here is when we exercise, the blood redistributes to the muscles, okay, and we limit the supply. So what we're going to do now is we're going to talk about the vascular shunt mechanism and talk about them words vasodilate, vasoconstrict, which I introduced in the structure of blood vessels, because that is ultimately what is the mechanism for this redistribution. Okay, so it's controlled by this vascular shunt mechanism, this redistribution. Okay, so as we know, arteries lead to arterioles. Arterioles lead to capillary beds. Now at the capillary beds, I didn't mention this in the last video, we have pre-capillary sphincters. And I'm sorry if I'm saying that wrong. Okay, so pre-capillary sphincters. And what they are is they're a ring of smooth muscle. So let's take a look at them. So as we can see there, we look at the aorta. The aorta takes on the right turn into the arteriole. And then as the arteriole is about to meet the capillaries, at the junction there, if you like, we have pre-capillary sphincters. And if you look there, you can clearly see from the diagram that ring of smooth muscle, its structure. Okay? And if we remember from the last video, these rings, these smooth muscle, like the arteries have a thick wall, they allow vasoconstriction and vasodilation. Okay? Because it's smooth muscle. So we're going to look at how this mechanism affects the redistribution. Okay, so these will ultimately control the blood flow through the capillary bed. Right, here we go. So as I just mentioned, blood flow is controlled into the capillary bed by the pre-capillary sphincters. And we know that one of the capillaries' function is they're slowing down that blood to allow gaseous exchange. But these pre-capillary sphincters decide the amount. So these sphincters, they can constrict. And when we constrict, we narrow that lumen. So this smooth muscle constrict, it narrows and it limits the blood flow through the capillary bed. That looks like this. So if you look at the blood flow, it's created its own channel there. And you have that greyish colour in the capillary bed, the majority of the capillary bed, because it's limited its blood supply. So then smooth muscle rings have constricted and direct the blood through that channel. So they limit the blood flow through the capillary bed. When they dilate, they widen. So we have that widening of the lumen due to the muscle, and we maximize blood flow. So you can see the difference in the diagrams there. Through all the arterioles to all of the capillaries, okay, we have maximized the blood flow through that capillary bed. Okay, so we've maximized the blood flow. So now we need to link this back to the redistribution. Okay, so let's focus on rest or recovery. Okay, focus on rest. As we know, 75% of this oxygenated blood needs to go to the organs. So what happens is the arterioles to the organs, we need to be very specific here not to get confused. This is at rest. The arterioles to the organs vasodilate. They increase blood flow. So they look like that with a wider lumen. The smooth muscle is allowing that to happen, that wall of muscle. The arterioles to the muscles. Now we only want the muscles getting 20% of the blood at rest. So they vasoconstrict and limit the blood flow. So you see there, the lumen is much narrower. We have constriction there, and the muscle wall there is contracting. It's constricting and narrowing and limiting that blood flow, okay, to the muscles. Now we have the pre-capillary sphincters. The ones to the organs dilate. So the pre-capillary sphincters dilate, opening up the capillary beds to the organ cells. So it becomes flush with blood. So we maximize that blood flow through the capillary bed because they are going to the organs which need 75% of the blood at rest. Now obviously the opposite is going to happen to the muscles. They constrict, they close to the capillary beds and create that channel to the muscle cells, so only giving around 20% of that cardiac output at rest. Now the next slide here is just complete opposite of this, okay, but we need to be very specific so we don't get confused. So now it's cardiac output during exercise. So this is where we have this massive redistribution of blood, and we're looking to get 88% of that blood to the muscles. But remember, that's the highest amount at the most intense exercise, going towards that heart rate maximum. So the arterioles to the organs this time, they are the ones that vasoconstrict. So we're going to decrease the blood flow to the organs, so that narrow lumen. Okay? The arterioles to the muscles vasodilate. Wider lumen, all thanks to that structure of smooth muscle. The precapillary sphincters constrict, closing the capillary beds to the organ cells. So that grey colour there, the channel, some down at 1%, 1.25%, so heavy restriction. And then the sphincters to the muscle cells dilate. They open up and flush the capillary beds with blood. Okay, and this is the mechanism, these precapillary sphincters, that control this redistribution of blood flow. Okay, so this is what is happening. Now, I'm just going to add on here the vasomotor control to this video. So hopefully we understand there how the vascular shunt mechanism is working. But as we know from the cardiovascular system, we have a cardiac control center. Okay, in this we have a vasomotor control center. Okay, the VCC. Where is it located? In the medulla oblongata. The VCC is located in the medulla oblongata along with the CCC. Okay. The brain provides stimulation control to the precapillary sphincters. Okay, so just like the CCC controls cardiac controls heart rate, the VCC provides stimulation control to the precapillary sphincters. Okay, and this is why I've added it onto this video. So let's start with exercise. Okay, let's look at the vasomotor control in exercise. So here we go, neural, we should be going ding, 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 receptors, okay? Now the VCC receives information from the chemoreceptors. And what do chemoreceptors detect? Changes in chemical in the blood flow. So we're exercising, so we've got increased CO2 and lactic acid. We also have the baroreceptors working, and this is obvious, we're focusing on these blood vessels, okay? The arterioles, the capillaries, the pre-capillary sphincters, they decrease and increase stretch on the vessel walls. So, stimulation control from the brain, and that's going to send a message. So, this one here, sympathetic stimulation decreased. Now, if we're going to decrease the stimulation, that means we're looking to allow something to relax. And when the word relax gets used, we should think dilate. So, the arterioles and pre-capillary sphincters dilate. And because we're exercising, we're talking about the ones to the muscles. So blood flow increases to the muscle cells. So we have that neural control. They send information to the brain. The brain has stimulation control. And to the muscles, it decreases the stimulation to allow the pre-capillary sphincters to dilate and maximize blood flow to the muscle. So obviously on the other side, okay, there, a little diagram. So maximize blood flow to the muscles. But obviously on the other side, we're going to have sympathetic stimulation increased. And what that means is arterioles and pre-capillary sphincters constrict. And which ones are constricting? Well, if we want the blood going to the muscles, it must mean the blood flow to the organs. That is the blood that is constricting. Okay, so it would look like that. It creates that thoroughfare channel. Okay, because they're constricting. Now, the next slide again is going to be the opposite. So vasomotor control at rest. Now we have an increased O2 and a decreased lactic acid. The chemoreceptors have detected that. The baroreceptors have detected a decreased stretch on the wall. Okay, so that means we're resting or recovering. So we're responding to recovery here. We just finished the exercise. So the brain will give stimulation control. And on the left here, now the roles have reversed. So we're going to decrease the stimulation, but specifically the arterioles and pre-capillary sphincters of the organs. So these ones will dilate and blood flow increases to the organ cells. Okay, the blood flow is increased to the organ cells. Okay, and as we know, at rest or during recovery, we're only going to need around 20% going to the muscles. Okay, although it would happen slowly in recovery. The stimulation is increased. We want the pre-capillary sphincters to constrict. So that stimulation, that increase in stimulation causes that constriction, and the arterioles and pre-capillary sphincters constrict and limit or decrease blood flow to the muscle cells. So blood flow is decreased to the muscle cells. And ultimately that's how the VCC works. Very similar to the CCC. Sends stimulation, and when it decreases, that links to dilate, and when it increases, that links to constrict. Now, you'll always know which ones dilate and which ones constrict, depending on whether you're exercising or whether you're in rest or recovery. So the whole concept of this is this vascular shunt mechanism, this dilation and constriction of these pre-capillary sphincters, okay? But it's all about that redistribution of blood flow, increasing the blood to muscles during exercise. Okay, hope that helps. Thank you.